Kinematic equations. This is kind of a big one. We've taken our time getting to this point, but now we have some serious tools that we can use to attack problems. Constant acceleration motion gives us a whole array of problems we can solve. Actually, a lot of problems we do are constant acceleration problems, and these equations that we're going to do and this approach that we're going to do will work for all of those. In this video, I'm going to first develop a couple of kinematic equations, then look at them together, and finally give you a clean way to organize your thoughts and variables. I'll go through a couple example problems in separate videos, so if this feels a little bit scant, it's because there's more coming. Here we go. We can start with acceleration. We know acceleration is a rate of change of the velocity. We said acceleration is Vf minus Vi all over t. I'm going to write these as their scalar portions. We've been working in one dimension, so I'm just going to take everything to be vectorized, I suppose, by having pluses or minuses on those, which means I may not be writing vector hats on each thing necessarily. I can take this equation and rewrite it in terms of the final velocity. Here's that final velocity. I'm going to have that be the variable I solve for. So first, I'm going to identify this as my unknown. I'll write it in red. And now I want to isolate for Vf. So if I'm isolating for Vf, right now Vf is being subtracted by something, it's being divided by something. I'm going to have to get rid of that t first. What I do to one side of the equation, I have to do to the other. So now my left side says acceleration times time. I know it said t times a equals v final minus v initial. I want to get v final by itself, so I'm going to add v initial. That will get rid of those. I'm going to add v initial here. And I get v initial plus at equals v final. Or, because I kind of like to have my unknown on the left side, v final equals v initial plus at. That's an equation I'm going to use a lot, so I'm going to put a box around it. But this is pretty good. Given my starting point, in this case my initial velocity, and my acceleration, which is constant, I can find my velocity after a period of time. I'll run through an example, just a quick one. I'm on a train that's heading east at 30 meters per second. This is my train. The train needs to slow down so it engages the brakes, and the brakes can slow the train down at a rate of 2 meters per second squared. So my acceleration magnitude is 2 meters per second squared. How fast is the train moving after 4 seconds? So find v at t equals 4 seconds. I'm going to look at this, I'm going to say I'm moving eastward, I will call that my positive direction. If I'm slowing down, that means my acceleration must be in the opposite direction of my velocity. So my acceleration is actually going to be a negative 2 meters per second squared. Now I'm going to use my equation. This is my initial velocity, and I know my time already. I can use my equation. V final equals V initial plus a t. V initial is 30 meters per second plus the acceleration of negative 2 meters per second squared times the time of 4 seconds. Negative 2 times 4 is negative 8 plus 30 gives me 22 meters per second. I want to make sure that my time, or that my units actually work out. I've got meters per second here. I've got meters per second squared, which I'm multiplying by seconds. That drops, I'm left with meters per second. Now I can add these units, and it does work out to be the meters per second that I expect. Not too bad. I'll run through, again, more examples in a separate video. Heading back. I had this equation that I had been using for constant velocity motion, and it looked like this. I had x final equals x initial plus vt. And that thing assumed that I was looking at constant velocity. Now, I don't have constant velocity anymore. I'm throwing in acceleration so my velocity can change. I want to see what I can do with that. This equation, this one right here, will still work if for the v, I plug in an average speed. Now an average speed, that's going to be half of v initial plus v final. So I'm going to put that in for v. I get x final equals x initial plus half v initial plus v final that was my v average multiplied by time. Doing okay. However, a lot of the time I don't know my final velocity from the outset. I kind of know my initial velocity, I know the time, I can know the acceleration, that stuff I know, but I might not know my final velocity right from the beginning. So I'm going to take this whole expression that I had up here and I'm going to plug it in for v final. Right now what I have, before I do that, is this. I'm going to take that whole thing, that whole equation, and plug it in for v final. I got this by just distributing out these parentheses. So plugging that in, I get x final equals x initial, that part's easy, half v initial t, that's not bad, and I get a half v final. V final was v initial plus a t. So I get a half of all that times time. Again, all I did was plug into there. I'm going to again distribute this out. Alright, I've got this half v initial t, half v initial t. If I take those and put them together, I get a full v initial t. And that is an equation that I want to put a box around. That's one that's going to be helpful down the line. So that's two big kinematic equations. I can do one more thing. I can take this first equation back here, solve it for time, so isolate time, and then take that whole thing, plug it in down here, and do a little bit of rearranging. When I do that, I'm doing that just so that I can get time out of my equation, because once in a while that's actually a really helpful thing. So when I do that, I get this end result that looks like v final squared equals v initial squared plus 2a delta x. Remember, delta x is just x final minus x initial. That's an equation I'm going to actually end up using quite a bit. So I have these three equations that I'm going to use a lot, like a lot. So much actually that I'm going to call these my kinematic equations as a category, and I'm going to number them. The order that I've used for these equations is not the same as the order of the equations up above, as I'm sure you noticed. I numbered them in this way because this is kind of the order of frequency that you will use these. That first equation you will use probably the most often, the second one the next most often, that third one is kind of a, you'll use it definitely enough to make it worth knowing, but you'll use it probably less than the other two. There are a lot of variables in these equations, so seeing all this can be kind of a daunting thing. For me, instead of viewing these equations in terms of what's in there, I think it's actually a little bit easier to view these in terms of which variables are missing out of these. This first equation doesn't have any information about v final. The second equation doesn't have any information about x, and the third equation doesn't have any information about time. This together is a bit of information that I use so often that I want to set it aside and have it for easy reference. When I encounter a problem with constant acceleration, I like to make a quick table and I list off the different variables that show up in all of these equations. These are all the kinematic variables. I'm going to have x initial, x final, v initial, v final, acceleration, and time. I will, for a given problem, fill in which variables I know, which ones I don't know, and which ones it is that I'm actually going to solve for. Then, after I make that table, I write out my kinematic equation. So this setup right here, this is what the beginning of problems looks like for me. It's more work to set up all of these variables, to set up all of these equations, and to write this all out before even beginning a problem. But it gives you a starting point, which is really helpful. It gives you an organizational scheme so that right away you know what it is that you've got and what it is that you're looking for, and it'll very quickly give you the tools to be able to say, I know how to approach this problem, I know which equations to go to, and I know why. It means that, yes, it takes a little bit longer, but you can approach all these problems with confidence because this works every single time. I'll run through example problems in a couple of separate videos because this one's getting pretty long, but this is a good starting point.